The aircraft you fly on today is not built for metal. Not primarily. A Boeing 787 Dreamliner, the most widely flown wide-body aircraft in the world, is 50% carbon fiber composite by weight. 50%. The fuselage you sit inside, the wings generating lift, the tail surfaces controlling direction, the engine nacelles housing the most powerful turbofans ever built. All of it, a material that did not exist in any usable commercial form before 1963. A material that was nearly abandoned as a scientific curiosity before anyone understood what it could become. A material invented not for aviation, but for a race to the moon that nobody was sure humanity could win. And here is the part that makes this story genuinely extraordinary. The aviation industry, the industry that now depends on this material for the structural integrity of every wide-body jet, refused to use it for nearly 20 years after it was invented. The engineers who finally convinced Boeing to build an aircraft from a substance that had never been used for a primary aircraft structure before were told repeatedly by their own colleagues that they were going to kill people. They were wrong about that. But understanding why they were wrong and why the skeptics were not entirely unreasonable requires understanding exactly what carbon fiber composite is, where it came from, and what physical properties make it simultaneously the strongest and the most dangerous material aviation has ever adopted. Let me show you all three.
Carbon fiber was not invented. It was discovered, by accident, in a laboratory at the Royal Aircraft Establishment in Farnborough, England in 1963. Researcher Roger Bacon had been working with carbon whiskers, microscopic filaments of carbon, when his team discovered that heating polyacrylonitrile fibers under tension produced a material with properties that appeared physically impossible for its weight. The tensile strength, the force required to pull a given cross-section apart, was higher than steel, significantly higher. The stiffness, the resistance to bending under load, was comparable to steel. The weight was 1/4 of steel. To be precise, carbon fiber composite has a specific strength per unit of weight, approximately 5 times greater than structural steel, and a specific stiffness per unit of weight, approximately 4 times greater. These numbers violate intuition. Stronger and stiffer than steel, at 1/4 the weight, is not a property combination that occurs in nature. Every structural material that exists in nature trades strength against weight. Iron is strong and heavy. Bamboo is stiff and light, but not strong enough. Wood is light, but not stiff. Carbon fiber composite broke the trade-off entirely. It was simultaneously lighter, stronger, and stiffer than any structural material humanity had ever worked with. The question was not whether it would transform structural engineering. The question was why it took 30 years for aviation to fully trust it.
The reason aviation hesitated for 30 years, and the reason that hesitation was not irrational, is a property of carbon fiber composite that its extraordinary strength numbers do not capture. Metal fails gracefully. When a metal structural component reaches its stress limit, it deforms plastically. It bends visibly before it breaks. An engineer or inspector looking at a metal component under overload can see the deformation happening. The component warns you before it fails. Composite fails catastrophically. When a carbon fiber composite component reaches its stress limit, it does not bend, it does not deform visibly. It shatters, instantaneously, without warning. The full structural failure occurs in milliseconds without any prior visible indication. And there is a second problem. Composite damage is invisible. A metal aircraft that has been struck by ground equipment, hit by hail, or subjected to an unusual stress event will show the damage: dents, scratches, visible deformation. A composite aircraft subjected to the same events may appear perfectly undamaged on the surface, while internally, at the microscopic level, the carbon fiber layers have delaminated, separated from each other, in a way that has significantly reduced the structural integrity of the component. This is called barely visible impact damage, BVID. It was, and remains, the central challenge of composite aircraft maintenance. How do you inspect for damage you cannot see? The answer required the development of entirely new inspection technologies: ultrasonic scanning,
thermographic imaging, X-ray computed tomography, that did not exist when carbon fiber composite was first proposed for aircraft use. The skeptics who said it was dangerous were not wrong about the properties. They were wrong about the timeline, about how quickly the inspection technology would catch up to the material's demands.
Carbon fiber composite was not the only material the space race accidentally delivered to commercial aviation. Titanium alloy, specifically Ti6Al4V, the alloy of titanium, aluminum, and vanadium that constitutes approximately 80% of all titanium used in aerospace, was developed for the SR-71 Blackbird program in the late 1950s and early 1960s. The SR-71 operates at speeds that heat its airframe to temperatures exceeding 300 degrees Celsius through aerodynamic friction. At those temperatures, aluminum, the material all previous aircraft were built from, loses approximately 60% of its strength. Steel can handle the temperature, but weighs 3 times more than aluminum, making an SR-71 built from steel too heavy to achieve the performance specifications it was designed to meet. Titanium solved both problems simultaneously. It maintains structural integrity at temperatures where aluminum fails. It weighs approximately 40% more than aluminum, but significantly less than steel. Its specific strength per unit weight, exceeds both aluminum and steel at the temperatures the SR-71 operates at. The classified SR-71 program produced the most advanced titanium manufacturing techniques ever developed, techniques that were eventually transferred to commercial aviation through a complex pathway of declassification, industrial licensing, and material science research that took 2 decades. Today, the Boeing 777 contains approximately 9% titanium by weight. The Boeing 787 contains approximately 15% titanium. Every component that must survive high temperature, high load, or high vibration environments, fan blades, engine pylons, landing gear attachment points, high-pressure compressor discs, uses titanium alloy whose manufacturing techniques trace directly to a classified Cold War aircraft program that nobody was supposed to know existed. The materials keeping you safe at 35,000 feet were developed to keep reconnaissance pilots alive at 80,000 feet, for reasons that were never publicly acknowledged until the aircraft itself was declassified in 1990.
The Boeing 787 Dreamliner, the aircraft that brought composite primary structure to mainstream commercial aviation, had its first flight on December 15, 2009, 46 years after Roger Bacon's accidental discovery in a Farnborough laboratory. The 46 years between the material's discovery and its first use as the primary structure of a commercial aircraft carrying passengers is not a story of slow progress. It is a story of the specific pace at which trust is established between material science and the industry that depends on materials being trustworthy. Every step between 1963 and 2009, the development of BVID inspection methods, the qualification of repair procedures, the certification of manufacturing processes, the accumulation of fatigue test data across millions of simulated flight cycles, was a necessary step that could not be skipped. Aircraft certification is not a bureaucratic obstacle to engineering progress. It is the systematic documentation that a material will perform as predicted, not just in testing, but across 30 years of operation, in weather and temperatures and loads and impacts that no laboratory test fully anticipates. The Boeing 787 composite fuselage has now accumulated over 100 million flight hours across the global fleet. The predicted failure modes, the delamination concerns, the fatigue crack propagation questions, the lightning strike vulnerability issues have been addressed, tested, certified, and managed exactly as the material scientists predicted they could be. The skeptics were right about the challenges, the engineers were right about the solutions, and the result, a 20% fuel efficiency improvement over the aluminum aircraft it replaced, a quieter cabin, a higher humidity cabin environment possible because composite does not corrode, a slightly lower cabin altitude possible because composite can sustain higher pressurization than aluminum, is a material civilization upgrade that passengers experience on every 787 flight without knowing it occurred. The substance that was not supposed to exist in 1963 is now the reason your flight is quieter, more comfortable, and more fuel efficient than your parents' flights were. Follow for more about the materials, the physics, and the engineering decisions hiding inside the aircraft you fly on every day.